welcome everyone to today's first lecture in computational finance. As you can see, this is the updated set of slides now for 2019. I will be uploading the slides bit by bit to my website, just to make sure that everyone has the slides way before we'll meet here in class. What do I want to teach you this semester, and what do we want to discuss this semester? Computational finance is actually a very interesting and relatively new field to finance. Again, my Outlook. For some reason it always pops up. And we'll start today with a short introduction to numerical analysis, the basics of numerical analysis, the basics of how numerical analysis can be used in finance and anything that is related to finance. And as you can see from the next bullet points from the outline, we'll talk a lot about portfolio theory, portfolio optimization. Then we'll go to asset models. And after having spoken about asset models, that is stochastic processes and models for modeling the stochastic behavior of asset prices, we'll move on to what is usually referred to by computational finance, option pricing. If you take a textbook on computational finance, it will usually only include sophisticated models for option pricing. Why? Because that's the field in finance that definitely needs a lot of mathematical modeling power. But as we will see, especially in portfolio optimization, some rather elaborate models from numerical analysis can also be used in other fields outside of option pricing. And after having spoken a lot about option pricing, we'll see and look at interpolation. That is still very general and generic. And afterwards, we'll talk about yield curves and yield curve modeling for interest rates. This is actually again, a part in finance where we need more complex mathematical models to arrive at nice solutions for practical applications. Now, I will just start with some pretty basic things on how the module is structured and where you can get all the necessary information about the class as a whole. As you've probably noticed, this is a 10 ECTS credit point module in the master degree in business administration. Again, my Outlook. I had someone from the IT department upstairs to check this, and it seems it hasn't been resolved. So sorry for that. It's a 10 ECTS point module. It consists of 3 distinct classes. We'll have this 2-hour lecture here, and we'll have 2 e-learning classes that accompany this 2-hour lecture. One tutorial is meant to show you and highlight some previous exams, some examples, and some tasks that you might again find in the final exam. And the third tutorial is just meant to teach you a little bit how you can model financial problems yourself in MATLAB or Octave. It's not relevant for the exam, but it can help you understand the problems we'll be dealing with here in class, and it will give you a little better idea how all these models and how all these things that we'll be discussing in this class can be applied in practice. No? Actually, computational finance and this intersection between numerical analysis and mathematical modeling on the one hand and finance on the other hand is quite practical, because it's something that you will be needing a lot if you want to work as a quantitative analyst or as a quant specialist in finance and in trading. Yeah, it's an elective course, so no one's forced to take this class. Keep that in mind, and it will end with a written exam of length 90 minutes. Okay. If you go to the course website, you will probably all have discovered the course website now under teaching on my private website. you can see some general information about the class, and here you will have the link to the set of slides. The slides are still available in German, but they are outdated because we are redoing the whole set of slides this semester. There will be a large part of slides that are no longer in use in the German script, and some new slides that will only be available in German. But if you think you need the German slides, at least for say 80–90% of the class, you can have a look at the German slides. There are some. There's one Excel sheet and a MATLAB program already on the website. We'll be uploading maybe a couple of more programs and data sets, so you can use these data and these programs yourself in MATLAB. And the tutorials in MATLAB, Octave tutorials, those tutorials will come later this semester. We'll have a bunch of previous exams, a student evaluation if you're interested in what your predecessors thought about this class, and the information for our Erasmus students. You can take the written exam, or you can write an Erasmus paper. Same rules. It has slightly changed. The deadline is July 26, and please hand it in via email to our secretary. Yeah? And you can see the link here and the deadline as well. Okay. In this class, it might be a little bit different because in computational finance, one could also think, when it comes to the Erasmus paper, one could also think about a modeling task. That I could give you a data set and you're asked to write a program in MATLAB and write about how you have modeled the data, what are the results, what can be how these results can be interpreted. So it could be a little bit different from the ones you've previously written in the last semester. Okay, that's the course website. Now let's go not yet to Twitter. Yeah, Twitter is next. I now have a Twitter account, and I don't want to spam you with my personal opinion, but I may be interested to retweet some information from things I found interesting from the ECB, from politicians, from other fellow economists. Professor Schnabel is on Twitter, and he tweets a lot. So I might retweet some information or send around some information on current research. You don't need that, but if you are interested in having a glance at what research and economic policy is currently working on and discussing, you might want to add me on Twitter. YouTube. Just like this lecture, all lectures are recorded, uploaded on YouTube. If you want to be informed when a new video has been uploaded, just subscribe to the YouTube channel, and you will be notified when new videos are available. Obviously, everything that is relevant for the exam will be discussed here in class, and will also be recorded. There should not be any discrepancy between the information you are given here in class and the information that is available in the videos. However, as soon as someone asks a question, and as soon as it might be again that personal rights and privacy rights might be infringed, I will cut these parts out of the videos. So if, for example, someone of you asks a question related to the exam, it might be that I'm forced to cut this out, and then it will not be in the video. So don't be surprised if there is some information, if someone asks a question here, that will not be in the videos. I'm just telling you this because it might be that you think, oh, okay, bye-bye, I just watch the videos at home and you'll see me at the exam, and afterwards you might hear something, oh, in class we discussed this or that, and that wasn't in the videos. Okay. We have two mailing lists. Let me first check. Is everyone registered in AlmaWeb? Okay, so this shouldn't be a problem. There are some faculties that do not use AlmaWeb, I think. And in some cases, I will be sending around information via a message on AlmaWeb. So the best way to make sure that you get all information, for example, if I'm sick and I cannot give the lecture, the best way to keep informed and stay informed is to subscribe to the general mailing list of our chair. That's at Banken. Just if you click on this link here, you will be taken to the mailing list of the university Banken at lists. And so on. And we also have a second one that is Jobs Bank Fin for job postings, internships, student positions, trainee positions, and so on. All the job postings companies send to me, I will just relay them to Jobs Bank Fin. If you're not interested, don't subscribe to it. Okay. Those are the mailing lists. And now, if you want to get in touch with me and want to contact me, you can write me an email, advice@vifa.uni-leipzig.de, or you can schedule a meeting either in person or via Skype by following this link to Calendly. Calendly is a nice tool. It's directly linked to my Outlook calendar. Probably that's the reason why it keeps popping up. You can use Calendly and you can choose a consultation hour in my office, or you can choose a Skype call. Just open it up and you will see the times that are available. And here you can see, for example, a Skype call Monday on Friday. Choose a time and it will be directly inserted into my Outlook calendar. Yeah? And every time I'm not available, well, I will update Calendly accordingly. Okay, that's, I guess, pretty straightforward. It's just a nice tool. Okay, what can you expect of the exam? You will be, the best way to get an idea of what the exam will look like is just to look at the previous exams. I mean, we have like 5 or 6 old exams available for downloading on the website. That's the best way to see what the exam will look like. You should be able to master general formulae passively, in the sense that you important theorems and important results, you should be able to at least state the economic interpretation and the economic meaning of this theorem or this result. At least you should be able, if you are given a formula or if you are given a model, to describe what it does, what it is intended to do, what problems could arise. But you will see this if you look at the previous exams. I am a big fan of exams that cover all aspects of a lecture. Why? I still remember my old exams, actually the ones before my generation, so 1 or 2 years before I graduated. Those poor fellows, they had old diploma exams, and those exams read like, for example, in insurance, the German system of health insurance, full stop, 5 hours. That was the whole exam, and it was one-fifth, I think, of the final grade. That was the exam, that was the question. The German system of health insurance, full stop, 5 hours, start. Okay. And I don't like this type of exam and exam question. I will try to give you smaller questions, but I will try to cover all areas in the lecture. So if you realize that you haven't learned a part of the lecture, the exam will not be a complete default, but you will only have to skip, let's say, 5 points out of 90. Yeah? Okay. Some questions will be discussed in the online tutorial, and you also have the past exams. And there is always one 10-point, that is 10-minute question with a MATLAB Octave program. You will be given a program that is void of any hint at what the program might do, and you are asked to interpret the program, to say what it does, what the results should be, and what its intended purpose is, and what problems are associated with this program. So that is why you do not need to know MATLAB actively. You do not need to be able to program in MATLAB, but you should be able to read such a program and say what it does. And after having gone through the whole lecture, you should be able to do this. But as with any programming language, it's always easier to actively use the language than just to passively try to understand what it does. So if you've written a MATLAB program once or twice, it would definitely help you to understand what these programs do. Textbooks. Most of the lecture is still based on this book by Paolo Brandimate, Numerical Methods in Finance and Economics, a MATLAB-based introduction. Also, it's based in part on the previous version of the Albrecht Maurer textbook on investment and risk management. There are some additional books, like Applied Computational Economics and Finance, and here you will see how the definitions of computational finance differ. In some cases, computational finance will just be option pricing. In some other cases, computational finance is understood as finance and economics every time you have a number. Yeah? Every time you see a number in finance, it's already computational finance because you need at least a calculator to work with that. So this third book, actually, Applied Computational Economics and Finance, I don't really remember what approach they have. I just know it's not really option pricing. And then Paul Wilmot. That's a beauty. Paul Wilmot is a very interesting character. He used to be an instructor or lecturer, I think, at Oxford or Cambridge. He has undergone the archetypical education for a quant. I think he majored and did his PhD in mathematical physics, never had any contact with finance. And what does someone do who has studied and graduated in mathematics or in physics? Either unemployed or maybe go to the CERN, and everyone else goes to finance and investment banking. And he became a trader and an investment banker. He worked, I think, at Oxford or Cambridge. And then he became a trader, a quantitative analyst. And then he realized the need for a more scientific approach to these quantitative finance issues. And he founded a journal, a scientific journal. He also founded the first and only magazine for quants. And the journals and this magazine still exists. It's Wilmot. It has the same name as his last name. It's Wilmot. And he also wrote this book, Paul Wilmot on Quantitative Finance. I think it's 3 or 4 books on every aspect in quantitative finance. You do not need this, but if you are very interested in this, try to have a look at it. We might have it in the library. And the baseline here, in any way, is you do not need these textbooks. The Brandimate book is very interesting. It's very good, but I think it costs like 200 euros, and I don't think we really have it in the library. We might have. We have it? Yeah, but then probably just one edition and one copy. I don't think we have the money for more than one copy of this book. I know it. I once bought it. It's quite expensive. It's not 20 euros. It's rather 200. You do not need it. Everything you need is on the slides. And as you can see, we are aiming at round about 600 slides. So that's why I say everything you need for the exam is on the set of slides. Okay, financial modeling using MATLAB Octave. In this class, I'm using MATLAB and Octave. In a bit, I'll talk about what is Octave. MATLAB is a standard program slash programming language for mathematical modeling and for numerical analysis. You could also use Mathematica. You can also use R. MATLAB has the advantage that it's not open source. It's proprietary program. It's sold by MathWorks Inc. And MATLAB has some advantages, disadvantages over R. R, for example, has a clear focus on statistics and numerical computations in statistics. That's why, for example, in risk management, I'd rather use R. MATLAB has a stronger focus on matrix calculations and algebra and optimization. That's why it's called, initially was called MATLAB, Matrix Laboratory. So every time you need to do something with matrices, and especially in optimization, MATLAB is much better. Why? It uses basically the same set of algorithms and models that are also available in R, but it's much more tuned. The algorithms and functions are much better versed for a professional use in optimization than in R. In R, it depends on what package you're using. If you have an older, sophisticated package in R, it's okay. If you use new algorithms in new packages, it might be that these are still full with bugs and some programs might not be as efficient as other ones. The downside is MATLAB is quite expensive if you want a full license, but you can get a student license. The alternative is use Octave. Octave is the open source variant of MATLAB. It's not as fancy as MATLAB when it comes to graphics and plots, but for our purposes, you can just use Octave. So you don't need to buy MATLAB. I would also say the syntax of the language is almost 99% identical. So if you don't want to spend money, use Octave. Okay. I've already talked about the main objectives of this course. Numerical calculations, numerical analysis in finance, option pricing, and some other things that are related to portfolio optimization, convex optimization, and to give you a general understanding of why we need this and why things change and things turn out differently as soon as you start using a computer for real-life problems. So far, if you have only taken a basic class in finance, it is likely that you are aware of most of the traditional classic models in finance, Markowitz portfolio theory. You can calculate a net present value and so on. You can use interest rates. But as soon as you try to enter the real life and try to handle real life problems, you will be dealing with much larger data sets. You need to use a computer. You cannot no longer use a sheet of paper and make your calculation with a calculator, but you need to use a computer. You might be forced to use a computing grid because you need more power, and you will be handling large data sets. And I'm not yet speaking about big data and artificial intelligence, but I mean, this is obviously the direction we are heading into. But even with a regular sized Excel sheet, say with 50 megabytes of data, you can no longer use your own calculator, but you need to use a computer, and then problems immediately start to arise. Okay. And then term structure models, polynomial and spline interpolation, and matrix decompositions maybe as well. Okay. Any questions concerning the course outline, the basic setting? Okay. Then let's start with some introductory and hopefully motivating problems and things we'll be dealing with. Again, computational finance in the traditional sense is option pricing for exotic options and pricing of exotic structured financial products. Does everyone know what a structured product is? A financially engineered structured product? No. Okay. A basic financial product is a stock, is a bond, is a plain vanilla derivative. But if I were, let's assume I'm an investment fund. I need a certain cash flow for whatever reason, usually hedging. And I say, I need 108 minus 20, and I want to pay a price P for this cash flow. This is not a stock, it's not a zero coupon bond, it's not a regular bond, it's not a derivative, it's something else. So what can I do? I can go to a market participant, usually this will be a bank, an investment bank, and the investment bank will tell me, we are able to offer you a product that is structured to your needs, to this particular set of cash flows, and we'll be able to offer you this product for a price of, say, 128. And then I can buy it or I can not buy it. But what is happening in the background? The investment bank will say, okay, what does this look like? It looks like a bond plus a derivative plus maybe an investment in a risk-free asset, and it will structure this cash flow wanted by and asked for by the other market participant by combining more elementary and more basic financial products. And in the end, the investment bank will use maybe a derivative, an option, a swap contract, and a bond, and this together will be included in this contract. The investment fund, however, it will not buy one derivative and one bond and so on. It will only buy one contract, one structured finance product from the investment bank, and then it's the job of the investment bank to see how to make a profit by buying and selling all of these basic products. But here, obviously, if you have such a structured product, pricing will get more difficult and more difficult as you put more complex basic derivatives and financial products into this. And this is financial engineering. You're creating new types of financial instruments by combining more basic ones. And in the end, you're interested in pricing these products. You need to find the correct price. And that's what a financial engineer does. And as soon as this becomes more difficult, you need elaborate models from computational finance to price these products. Okay. Now, on the other hand, what is numerical analysis? Numerical analysis, the German word is Numerik, numerische Mathematik, or numerical mathematics. Numerical analysis is what? It's the subfield of mathematics that looks at problems where you need to find approximate solutions, where you cannot solve an equation or a problem analytically, meaning that, for example, you have an equation that looks like this, x plus 5 equals minus 10. Well, you can solve for x analytically, and you can find the exact solution of x. But in some, and in many cases, you cannot solve analytically for a problem. What is this? It's the exponential function. We'll later see how the exponential function is defined. It's defined by an infinite sum. And an infinite sum, by definition, well, it will converge to some value, but you will not find an exact value. Yeah. And in mathematics, there are many cases where you cannot find the exact solution, but you can only find an approximate solution. And this is where you need methods from numerical analysis. Okay. And to highlight these problems, we'll start with a very small and very instructive example in MATLAB. I talked about MATLAB already. I think this is quite clear. By the way, one advantage of MATLAB is also that it uses standard libraries. For example, LAPACK. That's a famous package of highly tuned algorithms for solving linear equations. And most of these algorithms are actually decades and sometimes centuries old. And they are programmed and available in languages, in programming languages that are quite old, but also still quite fast, like Fortran. And MATLAB uses some Fortran and some C functions and packages, and that's what makes MATLAB quite attractive, because it's quite fast. Okay. That's how MATLAB looks like in its main screen. But I can also, because I have MATLAB, I can also start it right now and show you what MATLAB looks like. It's the syntax of the language is extremely simple. This is the same screen, but the resolution is not very high. Okay, so this is MATLAB. You will just start, and you can start by saying A equals 5. Then B equals 10, and A plus B, and the answer is 15. These are the first steps in MATLAB, and as you can see, it's far from hypertext languages, it's far from C, it's far from Java. It's not really a programming language. It's just basic mathematical notation with some syntax rules. And that's MATLAB. Okay, and you can see here on the right-hand side, you can see those are 3 variables. You can see the values, and it has become quite nice and user-friendly in the last years. Actually, I have only found out that MATLAB now looks like this when I got the license a couple of weeks ago. And you have some new things added to MATLAB 2018. Okay, so that's MATLAB in higher resolution and in action. Now let's start with a very famous example, the Black-Scholes model. Does everyone know what the Black-Scholes model is, what it looks like, and what it does? Who does not know what the Black-Scholes model is? Okay, everyone knows the Black-Scholes model? Good. The Black-Scholes model, in essence, gives you an analytical solution for the option price of more or less a plain vanilla option. As soon as it's an exotic option, it is highly likely that the Black-Scholes model cannot be solved analytically, but in the plain vanilla case, you will get an analytical solution. What does this solution look like? Well, under the assumptions of the Black-Scholes model, you will have a pricing formula that looks like this: the price of a call option, European call, no dividends, etc. Pays, or should look like the current stock price times ND1, that is the standard normal cumulative distribution function at point D1, minus the strike, discounted continuously with interest rate R over the maturity capital T, times the standard normal CDF at D2. And D1 and D2, for some reason, if you know the model, you can see why D1 and D2 turn out with these expressions. This is the pricing formula. Okay, so we have strike price, the standard normal CDF. By the way, this is the distribution function, and a PDF is a probability density function in German. The CDF is the Verteilungsfunktion, the PDF is the Wahrscheinlichkeitsfunktion oder Dichtefunktion. So this is the CDF of the standard normal distribution. So far, so good. Problem is, as you can see, even though the Black-Scholes model gives you an analytical solution, you still need to compute this: n at D1 and n at D2. Now, I do remember quite vividly how this was done, say, 50 years ago, because I still remember the story of my my mother and my grandfather. My grandfather studied mathematics in the 30s in Berlin. At that time, I think he studied I think the Prussian Institute of Technology, or how it was called, later became the Technical University, but well, it was in the 30s. He studied mathematics, and in the 60s, when he bought his first own calculator for the equivalent of almost 1,000 euros, he took out his old books and he recalculated the tabulated values of the normal distribution with his calculator. Because almost 50 years ago, and going back centuries, mathematicians used to calculate and approximate these values, and they wrote the results down, say with 10 decimal points or 8 decimal points in large books. Go to our university and you can look up these old books where you can find the values of the cumulative distribution function and density function of the normal distribution. This is how mathematicians did it before the time of computers, because you cannot calculate it in an exact way. There's no analytical solution for this. So you need an approximate solution, and this is where numerical analysis comes into play. Next, as you can see, you have the exponential function and you have an integral here. And both these mathematical objects, these functions, cannot be solved in this case analytically. So again, you need actually to make two approximations to get the value of nd1 and nd2, of course, as well. We will later see that some methods and some algorithms are better or worse at performing the task. We will see that these numerical methods differ with respect to stability, efficiency, and also their convergence speed, and what we will later refer to as the condition of a problem. And last but not least, the computer itself can cause problems, which we'll see in the next very simple example. We'll look at a very simple expression that is 9 times 8.1 plus 8.1. Now, analytically, this is very simple. This is just 10 times 8.1, so the result should be 81. Nothing more, nothing less, 81. We'll do this in MATLAB, and note that we will stick to the rule that we use a decimal point and not a decimal comma like in German. Yeah. So it's 9 times 8.1 plus 8.1, and the answer is 81. With 4 zeros, but 81. Okay, so everything seems to be fine. Well, it's not. Next, we'll look at the function fix in MATLAB that rounds the argument to the next natural number. So fix 4.1 is 4, and fix 4.9 is also 4. So it rounds down to the next natural number. Now, let's do this here. We'll use fix 9 times 8.1 plus 8.1. And what is the result? It's not 81, as one would expect, but it's 80. So something's completely gone wrong here, and my computer, and your computer as well, is not even able to calculate 10 times 8.1. So we don't need to talk about integrals. We do not need to talk about Black-Scholes models. Our computers are not even able to calculate 10 times 8.1. Yeah? 81, 80, slight difference. You know? So the question is, what goes wrong here? Let's see what happens if we first set the rule, or this option, format long, meaning that the format of the expressions and the results displayed in MATLAB now do not use just 4 decimals, but in this case 2, 4, 6, 8, 10, 12, 14, 15 decimal points. So what comes out of this here, you can see actually, if we calculate 9 times 8.1 plus 8.1 in MATLAB, the result is not 81, but 80.99999999986. And then, if we round down to the next natural number, obviously the result will be not 81, but 80. So it's not fixed, but it's already 9 times 8.1 plus 8.1 that's causing the problem here. Why? Problem is, in a computer, all numbers are represented in the binary system. The computer can only calculate with ones and zeros. Current, no current. Yeah? 0, 1. True, false. So all numbers are represented not in the decimal system, but in the binary system. And the problem here is that some numbers that seem harmless in the decimal system are tricky in the binary system. And 8.1 is harmless in the decimal system, but it's tricky in the binary system. And then what happens? 8.1 is transformed into a binary, into the binary system. In the binary system, 8.1 does not have a finite but an infinite representation. And an infinite representation needs to be cut off at some point because the computer, in German I usually say, Computer kann nicht unendlich. Ja? Unendlich kann der Computer nicht. The computer cannot, and we as well, we cannot handle infinity. We cannot work with something that is supposed to be infinite. We can only work with finite numbers, with a finite number of decimals, and at some point we have to stop. And this is what is happening here. The computer transforms 8.1 into the decimal system. It sees that it has an infinite representation. It will cut off at some point, and then you will have a rounding error or a truncation error. And this is what happens here. And the result is that 9 times 8.1 creates a truncation error, plus 8.1 creates another truncation error, and then after 14 decimals, you will have a slight error. If you only look at 4 decimals, this error will not pop up, but you need to switch the display to format long to see that after 14 or 15 decimals, then suddenly a slight error occurs. Okay, that's the problem here. By the way, this will be explained in more detail in the tutorial, in the online tutorial. This is closely related to what is called the machine epsilon. Does anyone know what the machine epsilon is? Every computer has more or less a smallest number, a smallest precision with which the machine, the computer, the CPU can work. And if you have a high-end computer, it might be that the computer can work with 32 or 64 decimals, and that all calculations will be exact up until the, let's say, 16th decimal point. If you have a very cheap, if you have a very old computer, it might only be, for example, if you take your calculator, it might be that it can only calculate up to 8 decimal points with precision. And that is more or less basically what the machine epsilon tells you. How exact, what is the precision of all calculations done by this computer? And the machine epsilon can be more or less also seen here. It looks like that with this very simple calculation, after 15 or 16 decimal points, the problems start to rise. You can increase the machine precision, and you can use what is then called double precision and quadruple precision, and this is in the end how high-end computing machines and computing grids and computers will differ. I mean, your own personal PC and your own personal computer will be quite nice and will be quite good. And I'm not talking about a computer for professional gaming, but scientific computers will differ with respect to the precision for these calculations. It will only mean that these rounding and truncation errors will not pop up after 16 decimals, but say 128 decimals. And that's the important difference here. That's the machine epsilon. Okay, so computers cannot calculate 10 times 8.1. What else? Let's look at this simple linear system of equations. Lineares Gleichungssystem in German. We'll always write a system of linear equations in the matrix notation. H times x equals b. X is the solution vector. We are interested in solving for x. We have a matrix H and vectors x and b. And now H shall be what is called a Hilbert matrix. A Hilbert matrix has, of dimension n, has this prescribed special structure. It starts with 1, 1.5, 1/3, 1/4, and so on. So the easiest Hilbert matrix looks like this. That's a Hilbert matrix of dimension 2. Now, if I gave you a vector b, let's say 3 and 5, you can solve this system of linear equations on a sheet of paper. Okay, you don't have to do this now, but let's reverse engineer the problem for a moment. Let's assume I know the solution. And as a solution, I now take x to be 1, 2, 3, 4, 5, up until n. I calculate the vector b that should give me exactly this solution, 1, 2, 3, 4, 5, 6, and so on. This is what I'm doing now. H is Hilb 20. It's a 20-dimensional Hilbert matrix. X is a vector. That's why it's written in parentheses. This transposes the vector. 1 to 20 means that we are filling this vector with numbers 1, 2, 3, 4, 5 up to, until 20. And then that's what I mean with reverse engineer. B is x times h. And then I try to solve for this vector x again by writing h dash b. And this operator is the operator in MATLAB for solving a system of linear equations with h as the coefficient matrix and b on the right-hand side. And as you can see, solving this system of linear equations results, first of all, a warning. Matrix is close to singular or badly scaled. Results may be inaccurate. And well, let's see what comes out. 1. From our previous example, we already know that if you see not 1, but 1.0000, this means that probably after 10 or 15 decimals, there's a slight there's a number that is not equal to 0. So it's not exactly 1. 2.0011, well, slightly off. 2.9574, not even close. And if you go down, line 13, the correct result would be 11, and matrix gives you the result 202. By far not the result we are looking for. This is a system of linear equations. Apart from the fact that it's 20-dimensional, if I have given you it in 5 or 3 or 2 dimensions, you could have solved it analytically with no problem, just a small hassle for you on a sheet of paper, and you would have gotten the correct result. MATLAB hisses a white flag. It only gives you a warning that the matrix seems to be badly scaled or badly conditioned, but the result is not usable at all. It's completely off. Okay. This is an example of error propagation. and of a badly conditioned problem. Here, it's not the problem of the algorithm. The problem is that any algorithm that tries to solve this particular problem will fail. And you need to change the approach to the problem in order to solve this system of linear equations. It's what is called a badly conditioned problem. We'll later see what bad condition means. It more or less means that a slight error in the input data will be propagated and will be scaled up to an even larger error in the output data, in the result. And this is what happens here. And MATLAB issued a warning, but there are some cases where MATLAB will not even issue a warning. It will just calculate the result, and the result will be completely off. And this is, the Hilbert matrix is famous for this. The Hilbert matrix is famous for being badly conditioned when being used in a system of linear equations. Okay. So let's talk about some basic rules and some basics in numerical analysis. First, we'll start again with the decimal representation. As you can clearly see, if you have a number 1492 in the decimal system, it's represented as 1 times 10 to the third, plus 4 times 10 squared, plus 9 times 10, plus 2 times 10 to the 0th power. Decimal places can also be depicted and represented in this way. You just take 10 to the minus 1th power and so on, minus 2th power. Some numbers, as you remember from school, in the decimal system do not have a finite representation. 1/3 is 0.33333 and so on for all eternity. The same in the binary system, just the problem is some numbers in the decimal system that have a finite representation switch to an infinite representation and vice versa. So 21.5 is 2 to the 4th power plus 2 squared plus 2 plus 2 to the minus 1 power, and that gives you 10101.1 in the binary system. Finite representation, but 8.1 or 0.1 or 0.5, all these numbers, they will look like this. 0.7 is 0.1 and then 0110 period, and this goes on. That is why the computer needs to cut off 8.1 at some point, and that's why you get a truncation error here in this case. So you need to cut this from a certain place on, and you will get a rounding error. And this seems counterintuitive at first. We use 10 times 8.1, and if I told you, well, the computer cannot work with 8.1 because of a rounding error, you would at first say, well, why is this a rounding error? 8.1 is 8.1. Well, not for the computer. Then, some mathematical expressions are given as an infinite sum, like the exponential function, and the computer, again, cannot work with such an infinite representation. It will need to cut off this infinite sum at some point, and then you get what is rather called a truncation error. This is also closely related to the phenomenon of cancellation. Cancellation is what? You have two numbers that are close in absolute magnitude, but differ in its sign. For example, 123.4 minus 123.5, or 123.4 minus 123.5. Same here. 2.345678 and 2.346789. And if you compute this with 246 decimals precision, you will get the exact true solution 0.001111. But if you only compute it with 2 places of exactness, the result will be 0. And it's not a problem that the absolute error is enormous, but cancellation means that the relative error, so the error in comparison to what you were expecting, is extremely high. And that's cancellation. In German it's called Auslöschung. Auslöschung führender Stellen. And in this case, you would also, if you see this result, you would see, oh, these two numbers match. They are identical with in absolute figures, but they only differ in sign. Well, they do not. They differ at the 5th or 6th decimal. And if you only have 2 decimals exactness and precision, well, this error will not pop up. That's cancellation. And coming now to algorithms, you can also look at the stability, efficiency, convergence, and condition of an algorithm or a numerical problem. Let's look at these concepts. We'll start with stability. Just in general, we'll have input data X. We'll have an algorithm F, and f of X will yield the solution Y. Okay. X, however, will almost always include some kind of input error. So we will have X bar, that is X, the true input data, plus an error, delta X. Now, what would you expect from an algorithm, ideally? Ideally, we would expect the exact solution being f of X bar. However, we will usually get Y star. Why is that? There are 2 sources of errors here. First, we'll have an error in the input data and an algorithm that adds another error. And in the end, you will see, you can only observe this, Y star. And it might be that the error in the solution is due to the input data, but it also might be due to the algorithm introducing another error. Is that clear? That you will get 2 sources of errors in these calculations. Ideally, you will have disturbed an erroneous input data, and if the algorithm is fine, you will get a false result. You will not get Y, you will get f X bar. But this here is what would come out if the algorithm works fine on data that already includes an error. Let's make a very simple example. Let's count the students here. Let's say we have 10 here. On the right hand side, let's say 8. And the data is now correct. And now I have an algorithm that computes the total number of students, and I will say, well, this is my algorithm plus, and the result will be 18. Okay. Now, if I miscount the number on the left-hand side, let's say the data is 11. What should I expect? If the algorithm is fine, I have to accept 19. This is not the 18 I'm looking for, but what kind of algorithm should this be? If I give the algorithm wrong data, but it still gives the correct answer. That should not happen. Garbage in, garbage out, but it should be the correct amount of garbage. Yeah? And then it could be that if I have input data here, and a false algorithm, it could be that I'm counting 10, I'm counting 8, but I get out 18.5 for some reason. And then could be if I have input data error, 11 plus 8, I will get 19.3 for some reason. I will have 1 error in the input data and an additional error that is added by a false algorithm or by an algorithm that is slightly off. And let's start with stability of a problem. Now let me just erase all this here. What is the stability of an algorithm? An algorithm is called stable if the relative error, and we now use a norm. You could also use absolute numbers. Just remember that, well, in mathematics, what is the absolute number of -4? Well, it's 4. What is the absolute number of 4? It's also 4. But what is, for example, a norm of a vector? Well, we'll learn this later on in this class. You can generalize the concept of a metric and a norm to vectors and matrices as well. And you might remember this from your school classes in geometry, that you can take a vector and you can take the absolute value of a vector, the scalar, more or less the scalar product. And it's supposed to be the distance to the zero, to 0 point. So f and x bar and y star and so on. This could be a number, this could be a vector, this could be a function, but we need to generalize the idea of an absolute value, right? And I'll make an example here. Let's assume we are expecting an input data error. So we will only use x bar. So f of x bar is what should come out of the algorithm, let's say 5. What actually comes out of the algorithm, and we'll take the absolute value of these two divided by what is supposed to come out. So that's again the absolute number of 5, the absolute value of 5. So in the end, we'll have 3 over 5. That's our relative error. We'll be off by 3 and we were expecting 5. So a relatively high relative error. And why are we taking the absolute value? Because we are not interested whether the result is higher or lower than we were expecting. Both are bad. Deviation above and deviation below. And the same can be generalized to vectors and matrices as well. An algorithm is called stable if this relative error has the same order of magnitude as the machine epsilon, and this is supposed to be the machine epsilon. So you take a number x, you round it with a computer, and the relative rounding error is smaller than epsilon. And as you can see, the machine epsilon gives you an idea of what the maximum rounding error will be. And the better the computer, the smaller the maximal rounding error, and the higher the machine epsilon will be. Or the better the machine epsilon will be. So this is the relative error, and this is the stability. What does it mean? An algorithm is stable if, and only if, what happens? If the additional error introduced into the problem by the algorithm doesn't grow too large. If the relative error introduced by the algorithm doesn't grow too large. That's the stability of an algorithm. Then what's the condition? Condition, we are looking at what we are expecting with correct data and what we are expecting with disturbed data, leaving out the correctness and the validity of the algorithm itself. So this is the relative error caused by faulty input data in comparison to what the relative error in the input data looks like. So on the right-hand side, we have the initial relative input data error. On the left-hand side, we have the relative error between what should come out with correct data and what should come out with faulty data. So this is the first part of the error. What happens if we insert wrong input data, leaving out what the algorithm adds on top? And the condition of such a problem is this sigma here. This is the so-called condition number, die Konditionszahl eines mathematischen Problems. What does that mean? If the problem is badly conditioned and if the condition number is very high, it means that you have a tiny error in your input data and it is scaled up, it's aggravated. The small error will explode in any type of algorithm if you try to solve this particular problem F. And it doesn't tell you anything about what comes out of F. It simply says that if you use X for problem F, just like in the example Hilbert matrix, solving for a system of linear equations, regardless of what type of algorithm you're using, if you're not solving for it analytically, the problem, any error in the input data will be driven up. And by the way, that happens with the Hilbert matrix. I didn't say anything about errors in the input data. Did we have data errors? With a computer, always. Rounding errors. You saw in the very first example that you will always have rounding errors and truncation errors in the computer. And actually these tiny errors in all those coefficients of the Hilbert matrix and all these computations, all these tiny errors led to a difference of this one solution, 11, compared to the estimated solution of 200. That's a badly conditioned problem. Tiny error in the input data, any type of algorithm, this problem goes completely out of proportion. It's blown out of proportion when it comes to this relative error. That's a condition. A different example, also a very simple one, more or less. We look at a polynomial, x to the 8th power minus 36 and so on equal to 0. We are now looking to solve for the so-called roots or zeros of this polynomial equation. In German, Nullstellenberechnung des Polynoms. In MATLAB, you can simply use roots and then put the polynomial coefficients in parentheses. MATLAB has the rule that you start with the coefficient of the highest order polynomial. So this is 1 times x to the 8th power minus 36 times x to the 7th power and so on. This is a little bit confusing because one would think that you start with 5 plus x minus 7 times x squared and so on. In MATLAB, it's the other way around. Yeah? So you have to count the number of entries in this vector to know that this is a polynomial with x of 8 as a highest order polynomial. Let's solve for the roots of P1. 8, 7, 6, 5, 4, 3, 2, 1. No coincidence. This is what I did. I simply took those 8 numbers, 1, 2 through 8, and I said x minus 1 times x minus 2 times x minus 3. Basic example from school mathematics. And then I calculated this by hand, and this is how I got the, actually I computed it symbolically with a computer, but this is how I got the coefficients. So far, everything's fine. Now, let's look at the condition of this problem. We want to solve for the roots. Again, the coefficients did not have any error. Only those tiny rounding errors that will occur anytime when using it in computer. Okay. Now, I've taken these coefficients, and as you can see, minus 36.001, a tiny error in the input data. And we are expecting 1, 2, 3 through 8, and the result is 1, 2.0002, 2.99111, 4.16, 4.57, completely wrong. 8.27 and 6.499 minus 0.7293i. Two observations. First, tiny error in the input data, problem gives you, and the algorithm gives you a result that is nowhere close to the solution. Second, we are not even in the field of real numbers anymore. You will see that here, these two numbers, they are not even real any longer. So it's not just that we have a slightly or more or less slightly off result, but the whole problem is no longer soluble in the set of real numbers, in the field of real numbers, but we are now in the complex numbers. Big problem, and just caused by a tiny error at the third decimal place here in the second coefficient. Famous example, by the way, does anyone study math or physics? Yeah. Well, this is a very famous example from numerical analysis. One would think that this is the problem of this particular polynomial. Why did you choose a polynomial of order 9 and so on? Well, no, bogus. In numerical analysis, you can easily show that polynomials and the roots of solving for the roots of a polynomial this way will always be badly conditioned. No matter how you want to solve for this, it will always cause the same problems. Does anyone know how to circumvent the problem? A very, very nice trick from numerical analysis. It doesn't completely solve the problem, but it is a good way. This is so nice here in Leipzig. You've all taken the math introduction with our math department, so you should all know what a linear space is, what a basis of a linear space is, what a linear vector of a vector space is, and what a change in basis is for a linear space. Everyone clear about that? Vektorraum, linearer Raum, Basis, Basisvektoren, Basiswechsel. From linear algebra, you should know that a linear space, linearer Raum, Vektorraum, does have infinite bases. Meaning that a basis for this vector room and this linear space, vector space, is 1, x, x2, x3, and so on. And with this basis, you can represent any vector. A polynomial is a vector. But I said that you have infinite bases, and you can switch from one basis to another. A second basis is the so-called Chebyshev basis. The Chebyshev polynomials, a special kind of polynomials. Actually, I don't know how they exactly look like. It will go something like this, 1, 2x, and so on. They will look slightly different. You can change the... By the way, does one know what this is called in German? You are studying mathematics, right? Einheitsbasis. Ah, oh shit. Ja, die Monombasis. Because these are monomials. This monomial basis. From switching from the monomial basis to the Chebyshev basis, the condition improves a lot. Yeah? And this is interesting. Why? You can try and try and try all your algorithms. The solution to get a better result is not trying another algorithm, it's changing the problem and changing your approach to the problem. And this is the famous badly conditioned root solving for polynomials in monomial basis. Yeah? Just switch the way they are represented and you can get a much better problem, but a much better solution. Is everyone clear what the complex numbers are? And now our students here in Leipzig, they are more or less forced to see and learn the field of complex numbers. Everyone clear about complex numbers, komplexe Zahlen? Okay, so on the next two slides, I just summarize complex numbers. The most important results on complex numbers are, I guess, First of all, the real numbers are a subset of the complex numbers. And you have something that is called the imaginary unit, I, that is 0, 1. And some characteristics. If you take the square product of I, it will give you -1. A famous and intuitively very absurd result that something that is squared can be negative, but in the complex numbers this works. R is a subset of C, and the fundamental theorem of algebra that in the complex numbers all polynomials of level n or degree n have n roots. So for example, the counterexample in R is x squared plus 1 equal to 0 doesn't have any real roots. In the complex numbers, it's I and minus I. So the imaginary unit I is a solution here for this root, for this root. And in our example, 6.4999 plus 0.7293i, these two solutions are complex. And this is always a bad sign in finance. We rarely have anything that is complex. In engineering, in physics, yes, you work with complex numbers. But here, in our real-life examples with real cash flows and interest rates and so on, we should not encounter complex numbers. And if an algorithm has to digress into the complex numbers to find a solution, you can be sure that something's off. And it's the same here. Okay, so these are the two complex solutions here. Order of convergence and complexity. Many mathematical problems can only be solved in iteratively, meaning that you have a set of iterations and you're trying to solve the problem iteratively. Famous example for an iteration and for an iterative algorithm. Any idea? It's a little bit outdated. At least in my childhood, I still need to look up numbers in the phone book. What can you do to find a name in the phone book? You can use a simple divide and conquer algorithm and do what? Take the phone book, cut it into 2 halves, look left I'm looking for, let's say, someone called Martin. If I see the left side ends with, say, G, I know the name Martin, starting with an M, is not in this part. So I concentrate on the rest. Again, divide and conquer, cut in half, look left, is the name in here? Okay, do the same. Otherwise, continue on the right-hand side. That's the simplest algorithm that uses iterations and tries to find a name in a phone book iteratively. Why is it iteratively? And is it iterative in nature? Because before starting, you do not know how many pages you have to open and you have to look up to find the name. It might be 10, it might be 20. By the way, this divide and conquer algorithm is quite quick. That's also why you would use it in real life. Yeah? If you have a big phone book and you would need to look up 200 out of 500 pages, this would not be your first choice as an algorithm, right? Oh, I just pulled out my cable here. So that's an iterative algorithm. And more formally, you will have xn. Those are the approximations to your solution. You are trying to find x star, and you have an iterative sequence of approximations. And ideally, you would expect that the sequence, Folge, of iterative solutions converges at some point to x star. and the speed with which xn converges to the solution x star, that's your convergence speed and the convergence of the algorithm. Like I said, this divide and conquer algorithm with a phone book has a high order of convergence. There are some algorithms that are much slower, right? They will converge, but then again, what use does it have if you have a phone book of, say, 500 pages and you need 400 tries to find the solution? You want an algorithm that finds the name after 5 solutions and 5 approximations. Then you have a higher order of convergence. More formally, we say that the algorithm is at least of a linear order of convergence if the following holds for a constant c and a natural number n. The difference in absolute numbers of xn plus 1 minus x star, so the error, the absolute error in the n plus 1th iteration is smaller than or equal to the error in the previous iteration, xn minus x star, times this constant c for all following iterations n larger or equal than capital N. What does it mean? If you are taking, if your relative error, or no, your absolute error from the previous iteration quickly becomes smaller and smaller, you will have a higher order of convergence than in the case that you have this error that is quite large and only grows smaller with more and more iterations. For example, the order of convergence is quadratic if there is a constant for which we have error in the next iteration is smaller than constant c times the squared error in the previous iteration. Okay. You can distinguish and differentiate between local and global convergence. Global convergence means that it doesn't matter where you start. This algorithm with the phone book is globally convergent. You will always find the name you are looking for, regardless of whether you start in B or in C or in G or at X. A locally convergent algorithm would mean that if you want to find a name like Martin in a phone book, this would mean that your algorithm can only find the name if you start at, say, L, M, or N. That would be a locally convergent algorithm. And you will soon see what this means in mathematics. Quite simply, if you have a function like this, and you're looking for the minimal value here, this could mean that if you start here, x1, you can find it. If you start here at x1, you will find it. But say if you start here at x0, you will not find it and you might end up in here. Then you will miss the global minimal point, the global minimum of the function, and it might be that your algorithm is not globally but only locally convergent. Very important distinction. Very good example for this is the Newton iteration. Newton iteration is a very simple way of solving a nonlinear equation, meaning that you have a function that looks like this. Let's assume this. And you will probably know that if this were a linear function, well, you could try to solve this on a sheet of paper. Now this is a nonlinear function. What do? You might have seen this already in school. You can use the Newton algorithm, the Newton-Raphson algorithm or Newton iteration. You only need to make sure that you can build the first derivative of the function. By the way, what is meant by solving this nonlinear equation? What does it mean, solving? Well, obviously equal to 0. Yeah? That's quite clear. Again, we are trying to solve for the roots of this nonlinear equation. and the Newton iteration is quite old, quite famous. What does it mean? You calculate xn plus 1 by taking the previous value, xn, minus the function at fxn divided by the value of the first derivative at xn. And we'll do this by, say, starting at 0.5. And we're trying to solve for our polynomial. Not a very fancy nonlinear function, but still it's a nonlinear function. Okay, this looks a little bit weird in MATLAB. We'll first need the polynomial P1. Again, with a slight disturbance in the second coefficient. x0 is 7.5. P1 bar is polyderivative. MATLAB has a built-in function to calculate the coefficients of the derivative of a polynomial, because, as you might know, the derivative of a polynomial is again a polynomial of order -1. And this is quite simple. In MATLAB, you only use this built-in function polyder. You can also use polyval, which gives you the value of a polynomial p at point x. And this is what we do here, the value of the polynomial of p1 at x0. And what we are doing now is we start with x0. We calculate xn plus 1, xn minus f at x0 divided by f derivative at x0. 1, 2, 3 iterations. And as you can see, we will get 7.00000010 and so on. 3 iterations, and we've already found one solution, 7. As you remember, the initial polynomial had 1, 2, 3, 4, 5, 6, 7, and 8 as roots. And after 3 iterations, the Newton algorithm will give you a very good close approximation to one of these roots. But obviously, because we started at 7.5, it didn't give us 1 or 2, but it went to the next, to the closest root. And it's rather simple to see that the Newton or the Newton-Raphson algorithm is locally convergent, but very quick. No? There's a quadratic order of convergence, and this is why we only needed 3 very simple iterations to calculate this approximation here. Okay. Okay, I've used up all my time now, and we have a small example with some cash flows next, but I think we can just do this next week. Do you have any questions concerning stability, order of convergence, relative absolute errors, these very simple examples to showcase you what numerical analysis entails? And if you have no questions, well then thank you for your attention and see you next week. Thank you.